All right, guys, Mr. Antonucci here, and in this video, we want to define a definite integral as a limit of Riemann sums. So here's our definition. Suppose f is a function defined on the closed interval a to b. We're going to divide the interval into n subintervals of width delta xi. So again, they don't have to necessarily be the same width. And we're going to choose a number u sub I within each subinterval. So you don't have to pick the left endpoint, the right endpoint, the midpoint. You can pick any number within each of those different intervals. You evaluate the function at that value and form the Riemann sum by evaluating the function at each ui, multiplying it by the width of each of those subintervals, and then adding them all up. Now, if we take the limit of the max of delta xi approaching zero, what that means is that we're basically taking the width of the largest subinterval that we pick and making it approach zero. Then, if that limit exists, we'll call it I, and it does not depend on the choice of the partition. So how wide we make each interval or not, because we're picking the biggest one and forcing it to go to zero, which is going to make all the other ones widths approach zero. And it doesn't depend on the choice within each subinterval. Then the number I is called a Riemann integral, or what we would call more formally a definite integral of f from a to b, and is denoted by this expression here. That is, and this is how we're going to read this, the definite integral of f of x from a to b dx is equal to the limit of the Riemann sum. So when this limit exists, we say that the function f is integrable over the interval a to b, or that the definite integral exists. So let's look at a little bit of the pieces of what's going on here. So we have this notation. It's an elongated S. The a and b are the limits. So a is the lower limit of integration, b is the upper limit. The f of x inside there is called the integrand, and the dx that closes it is the variable of integration. And this elongated s here is known as the integral sign. So a couple things that follow from this are that if f of a is defined, then the definite integral from a to a of f of x dx equals zero. So think about it like this. If I have some function and I go from a to a. Now, normally we go from a to b. All right, and then this would be the definite integral would represent the area of that region. But if I go from a to a, I didn't go over an interval, so there's no width, therefore there is no interval. Another thing that's important to note is that if a ends up being greater than b, then the integral from a to b is equal to the opposite of the integral from b to a. In other words, another way to think about this is if you flip the limits on an integral, then you're going to get the opposite sign as your answer for that. Okay, so first couple things we want to do with this are just learn how to switch between notations. So we're going to express this limit as a definite integral. So if we take the limit as the max of delta xi approaches zero of the sum I equals 1 to n of ui squared minus 3 delta xi, it's going to exist. And we can rewrite this as the integral from 0 to 6 of x squared minus 3 dx. Okay, the interval 0 to 6 came from the problem. That becomes the upper and lower limit. The function becomes the f of x right here, and your delta x becomes dx, which stands for an infinitesimally small change in x. Because if you think about it, The limit is saying that the largest width of all those subintervals is approaching zero. Okay. Excuse me. Not that it is zero, but that it's approaching zero. Therefore, it's infinitesimally small. Okay. So as a result, for regular partitions of an interval, closed interval a to b, the definite integral can be expressed in these two ways. Okay, the limit as delta x approaches zero, or the limit as n approaches infinity. This first one is saying that the width of each subinterval is approaching zero. As you make each subinterval get thinner and thinner and thinner, you're going to have to make more subintervals. So that's going to imply that you have an infinite number of rectangles approximating the area under the graph, giving you the exact answer. This second one is essentially saying that the number of rectangles is approaching infinity. Well, if you are letting the number of rectangles in a finite region approach infinity, that's going to imply that the width of each rectangle is getting infinitesimally thin or approaching zero. So what we're going to do now is switch back and forth. We're going to start with the integral expression and go back to a Riemann sum um, notation here. So for the first one, we're going to do delta x is 8 minus 0 over n, which is 8 over n. All right, so we're going to partition the interval 0 to 8 into n subintervals, each of with delta x. So, for example, the first interval is going to go from 0 to delta x. Then the next one's going to go from delta x to 2 delta x. Then the next one's going to go from 2 delta x to 3 delta x, and so forth and so on until we get to the last interval. The last interval has to end at n delta x. So that means it started at n minus 1 times delta x. Okay, so the right endpoint of the last subinterval is n times delta x, which is n times 8 over n, which would simplify to 8, as it should, because our interval goes from 0 to 8. So if I let u equal I times delta x, then the integral from 0 to 8 of square root x dx becomes the limit as delta x approaches 0 of the sum of I equals 1 to n of f of ui delta x, which in this case is sum I equals 1 to n. Oh, forgot the limit as delta x approaches 0 of f of I delta x times delta x, which is the limit as delta x approaches 0 of the sum I equals 1 to n of square root I delta x times delta x. Okay, so that's using this first expression. If we want to use the other expression, it's going to be sum 0 to 8 of square root x dx equals the limit as n approaches infinity of the sum I equals 1 to n of f of ui times b minus a over n, which is going to be the limit as n approaches infinity, sum I equals 1 to n of f of x of I x delta x, excuse me, times 8 over n, which is the limit as n approaches infinity, the square root of I over 8 n times 8 over n. Okay, that last 8 over n is not in the square root. Okay, so that was part A. If we do part B, okay, we'll do that up here. Part B, delta x is b minus a over n, so 8 pi minus 2 pi over n, which is 6 pi over n. So if we partition the interval 2 pi to 8 pi, the first subinterval is going to start at 2 pi, and then we're going to add delta x for the right endpoint. And then the next interval is going to start where the last one ended, so 2 pi plus delta x. And then we're going to add another delta x, or 2 delta x to it, so 2 pi plus 2 delta x. And then we're going to continue and so forth and so on until we get to the last subinterval, which is going to end at 2 pi plus n delta x. And it began one less than that, so 2 pi plus n minus 1 delta x. Okay, again, note that the right endpoint, if we plug in 6 pi over n for the delta x, you have 6 pi over n times n, which would be 6 pi, and 2 pi plus 6 pi is 8 pi, which is the endpoint of the entire interval, as it should be. So if we use the first expression, integral 2 pi to 8 pi of sine x dx, this is going to end up being the limit as delta x approaches 0, the sum I equals 1 to n of sine of 2 pi 2 pi plus 2 pi plus I delta x times delta x. If we use the second formula, or second expression, it's going to be the limit as n approaches infinity, the sum I equals 1 to n of f of xi. So 2 pi plus I times 6 pi over n times b minus a over n, which in this case is 6 pi over n. Okay, so either way. All right. So I know that was a lot there. But now we're going to talk about going the other way, express each limit of a Riemann sum as a definite integral. So the first one, we have the limit I equals 1 to n, square root 20 over ni times 10 over I on the interval 0 to 10. So let's take a look at that one. So I know that delta x equals b minus a over n, which is 10 over n. And if we partition the subinterval, we're going to go 0 to delta x, then delta x to delta x times 2. And then the next one's going to go 2 delta x to 3 delta x, and so forth till we get to the last one that's going to end at n delta x. And then the beginning of that one is one less than that, so n minus 1 delta x. So again, if we plug in 10 over n for n here, or for delta x, the n's would cancel and you'd have 10, which is the right endpoint of the last subinterval, which is the endpoint of the whole interval, which is 10, as it should be. So if I equals I delta x, then we would have square root 20 I over n times 10 over n equaling square root 2 times 10 over n I times 10 over n, which is square root 2I delta x times delta x, which is equal to 2 ui delta x. So then we could write that as the definite integral from 0 to 10 of square root 2x delta x. See, these middle steps, especially getting the 10 over n and the ui and rewriting it, helps us see that the integrand is square root 2x and not just square root x. Now for part B, okay, um, we have the interval going from, well, here, you know what? Let me erase this so that we have something to work with. Okay, so the interval is pi over 4 to 9 pi over 4. First thing we want to do is see what our delta x should be. So 9 pi over 4 minus pi over 4 all over n, which is going to be 8 pi over 4 or 2 pi over n. Then, since our interval begins at pi over 4, our subintervals, just write a couple of them out, is going to be pi over 4 to pi over 4 plus delta x. And then the next one's going to be pi over 4 plus delta x, comma, pi over 4 plus 2 delta x, and so forth and so on. And that helps us see that ui is got to be pi over 4 plus I delta x. It just helps us see the pattern. Okay. Then our expression is going to be sine pi over 4 plus 2 pi over ni, 2 pi over n, that's this right here. And that's going to equal sine of pi over 4 plus I delta x, which is sine ui delta x. So then we did all of that so that we could just write the definite integral, which is pi over 4 to 9 pi over 4 sine x dx. And that would be our answer for that one there. Okay, so we can generalize this process that we did here by saying that the definite integral from a to b is equal to the limit as delta x approaches 0, the sum I equals 1 to n of f of a plus I delta x times delta x, where delta x is b minus a over n. Okay, so that's it for this one. I hope that was helpful to you in understanding that pattern. Reach out if you have any questions.